Hi, dear students. Today we are going to study a very interesting topic of chemistry, that is reactivity of metals with oxygen, like how oxygen behaves when it reacts with metals and how metals behave when they react with oxygen. So, one thing that you must be worried, like there are a lot of metals in the periodic table or in chemistry, but don't be worried. We are not going to study a lot of metals because definitely at the moment we don't have time. So we would be studying mostly the reaction of four metals like sodium, zinc, iron, and copper with oxygen or their chemical behavior towards oxygen. So, how they are reacting with oxygen, like all these metals, sodium, zinc, iron, and copper, and which sort of oxides. Definitely whenever anything is reacting in or any substance element, it is reacting with oxygen, it is forming a sort of oxide, but which sort of oxide we are expecting here, and what are the properties of in these oxides, and how these can be formed, and which sort of properties they can show at the end. If we are looking into the elements, like as I was discussing that we are studying sodium, zinc, iron, and copper, so apparently there it looks like there is no link between all these metals, and these are quite random metals. So how we can compare these, because in comparison actually we are looking into some similarities and differences of these metals. So we can try to make a relationship or a, a sort of order between these metals by looking into the periodic table. So if you are coming towards the periodic table, you can see that the sodium atom or sodium metal, it is present in the very first group of the periodic table. If you are looking the other metals like zinc, iron, and copper, you can see like these metals or these elements are just present in almost, you can say, in the middle of the periodic table. So overall, if we are having a look on the position of these elements in the periodic table, you can see like these elements or metals are belonging to four different groups in the periodic table, and these four different groups are representative of different sort of chemical properties. Actually, each group in the periodic table, you may have an idea, is representative of a characteristic sort of chemical properties or chemical reactions in the periodic table. But if you want to have a more clear idea about the chemistry of these elements, you can have an idea like although they are present in the four groups, but actually they are belonging to two periods in the periodic table. You can say period number 3 and period number 4. And now, if you are looking into the period and group, you can say like maybe sodium is a bit different, but other three metals can be a bit closer to each other because they are belonging to a same period, and in period, properties are changing in a certain sequence, in a certain order, or following a particular trend. So now you can see like this sodium metal that is member of the first group in the periodic table, it can be a bit more different from all these three metals, but we can discuss the reactivity of all these metals in next slides, and you can see like how we can interpret this thing, like sodium can be a bit more different than other three metals. So one more thing that can help you to identify the properties or make a better comparison, like sodium is belonging to the S block elements, and in S block each and every element or metal, definitely it is having a characteristic electronic configuration where last electron is going to be in the S orbital. And if we are looking into these three metals which are situated in the middle, these are called, like these middle groups are called D block elements, and mostly the electron in the last shell, if you are trying to locate, it would be a d orbital. So last electron is going to be filled in the d orbital here. So this is a common property of all these three metals like iron, copper, zinc, all are having the last electron in the d orbital. Now we are trying to sort some more properties, like we got it like these are metals, we got it these are metals, but one thing like these are particular sort of metals that are called the alkali metals, because all these metals when they are dissolved in water they are forming strong alkalis, and like sodium when it is dissolved in water it is forming sodium hydroxide, that is a strong alkali that can neutralize the acid. And here one thing like we are checking the behavior of all these metals towards a common element that is oxygen, and oxygen is situated in the p block. And very interesting thing like all elements in the s and d block they are representing metals. Like metals can be different in properties, like here in s block elements metals can have a different reactivity, a different chemical behavior, but however these are metals. Similarly these transition metals can have a different category of metals, but however definitely they are metals. And these metals, all these metals, whether they are alkali metals or transition metals or d block metals, they are going to react with the oxygen that is a single element in the p block, and p block is carrying non-metals. So actually we are checking the behavior of reaction of these metals with this oxygen that is a non-metal. So now you can have an idea that in periodic table like metallic and non-metallic character has two different directions. Metallic character you can say it is towards the left side of periodic table and increasing in the same side, decreasing in this side, and non-metallic character is increasing towards the right side of the periodic table. So you got an idea that here everything is metal and here everything is non-metal. So actually you are trying to check the reactions of metals with non-metals. Like this is a common thing that can help you to compare the reactivity of these metals. And all these metals in the D block are named as transition metals, and these transition metals and alkali metals are now going to react with the non-metal that is oxygen. And whenever we are going to study a reaction of metal with non-metal, if you have already studied the chemical bonding, or maybe if we are going to discuss it later, like there could be a key for you for chemical reaction and chemical behaviors, that whenever metals are reacting with non-metals, an ionic bond formation is taking place actually. Why? Because metals are highly electropositive. They want to lose electrons and they want to be converted into positive ions or cations, so that they are called electropositive. But non-metals, like they want to gain electrons to complete their octet or duplet, so they are electronegative. They want to gain electrons and form anions. And when these cations and anions are going to combine with each other during chemical bond formation, an ionic bond is formed, because definitely here total loss of electron is happening and here gain of electron is happening, and mutual combination of both can result in the formation of ionic bond. So now we can check the individual reaction of each of this metal with oxygen. So for the very first metal that we are enlisting here is sodium metal, and now we are going to check the reaction of sodium metal with oxygen. So one thing, sodium metal is most common alkali metal in the throughout period of the periodic table. One thing, like you don't need to include this hydrogen, because you know hydrogen is having a contradictory behavior, like it has properties that are common to more than one group. So whenever I'm discussing this group one, except this hydrogen, mostly these alkali metals are having very close chemical behavior. So all are metals, all are hard, all are having metallic luster, and these are the common properties of all the metals. And among these, as we are particularly going to discuss the sodium metal, it is a soft silvery white metal. Its atomic number is 11 and its mass number is 23. So we can study its common behavior, because when we are looking into the alkali metals, you can have like have an idea that all the alkali metals, like uh, they are having one electron in the last shell, and they want to lose one electron in the last cell, or they tend to lose electron, and this is the key feature while they are reacting with any other thing. So sodium metal, like all other alkali metals, it is having one electron in the last cell as well, and it want to lose this electron to become an electropositive cation. So this white soft silvery metal tend to lose electrons like all other alkali metals. And this is a key feature, as I have discussed before. And why we are discussing it, like there could be a significance because it is the sixth most abundant element over the earth crust. Like oxygen is the first, then silicon, aluminium, iron, calcium, and at the end sodium is the sixth most abundant element on the earth crust. And not only on the earth crust, like it is most abundant element and that is dissolved in the seawater. It is also available in our daily life. It is like component of the table salt, sodium chloride, that is the major uh, component or major member of our daily kitchen life. So now one more thing that we got, like sodium is the member of highly reactive metals, because all are having significant size that is going to increase in a particular trend where shell is being added in each next member. But one common thing that you need to remember all time, last electron and plus one oxidation state. And this plus one oxidation state I can discuss a little bit more in next slides. And these metals are showing a lot of common reactions, but one of their most common reaction is with oxygen. So now we are going to discuss the most common reaction of sodium with oxygen, where sodium is showing the plus one oxidation state that can be written in the form of plus one charge over the symbol of the sodium metal. Like a later name of the sodium is natrium, so mostly the symbols of elements are originated from the first or some other letters from the later names. So from natrium you can see Na, and sometime the sodium name, it looks like it is originated from the soda can be a keyword to understand the properties of sodium hydroxide that we have talked before, that it can be produced when we are reacting or dissolving sodium metal in water. So oxidation state, even you can say that it is a charge that an element or atom or metal or non-metal or anything can show when it is uh, present in a complex form or it is forming a compound. As you can see, like in sodium chloride, sodium is having plus one oxidation state and chlorine is having minus one oxidation state. If we are coming to the oxygen, oxygen can have almost 7 different types of oxidation states. But here we are going to discuss the 3 oxidation states that are most common. So here it can be a simple oxide of sodium, peroxide, and superoxide. But with sodium you can have an idea, mostly the superoxides are not working well. Like peroxide and simple oxides, yes, they can be possible. Actually there could be some common behaviors, like where you can write some certain trends. Like for sodium, here you can add sodium at the place of X to understand the reactions of oxygen with sodium metal. And here, from here you can have a common idea of the reaction of these metals with oxygen. So if you are replacing this X, like sodium can be present at the place of X. So if you are placing X and then replacing sodium with X, you can have an idea of a reaction of these metals. So look at here, like although oxygen can show simple oxide, peroxide, superoxides, but for sodium, there are some definite oxidation states that can react with sodium. Like oxygen can react with sodium in almost two different oxidation states. Like it can either react in the form of peroxide or in the form of superoxide sometimes. So these two oxidation states of oxygen, you can say, could be working for the sodium. So simple oxide and peroxides can be working here. If we are overall categorizing the reactions of alkali metals with oxygen, you can have an idea all all other alkali metals like sodium can react with oxygen and it can show either oxidation or combustion. Both are actually reactions with oxygen, you can say, but in combustion necessarily some heat is produced. So if you can come here where you can see like this is the natural texture of sodium metal, and when it is exposed to air or left in the open air for some time, this metallic luster is lost and surface of metal is a little bit darkened. And this is not only the common behavior of this sodium metal, like other alkali metals can show this behavior as well, and this behavior is called tarnishing, or you can call it oxidation, because here oxygen is reacting but it is not necessary that heat is produced, so we can't call it combustion, so it is oxidation. So as lithium can react with oxygen, in the similar way oxygen can react with sodium and it can form either simple oxide or superoxide. But mostly this thing happens during combustion, during tarnishing, mostly like some oxygen is available. So this simple oxide is possible mostly. But as a result of tarnishing, you can see all the time metallic luster is lost a little bit. So mostly the metallic oxides are having a common behavior, like all metallic oxides are basic in nature. Like non-metallic oxides are acidic in nature because when they are dissolved in water, they are forming acids, but metallic oxides are basic in nature. So whenever this metallic oxide is dissolved in water, it is producing this sodium hydroxide that is a strong alkali, and that is called soda, as well as we have discussed before from where this name sodium has been originated. But for potassium, it can form some superoxides or something that may not be included in your topic, but yes, for your information, I have just added because most of alkali metals, like especially this lithium, sodium, and potassium, they are studied together and they have a lot of things that are common. So from here you got an idea that metals, especially alkali metals, can show frequent reactions with oxygen air, even at room temperature, ambient pressure, and things. So while we are transporting these metals and we are saving, we prefer to save them. And the mineral oils, where mineral oil can form a layer over the surface of these metals and can avoid their exposure to open air and avoid their tarnishing before their desired reaction is going to happen. So not only sodium, but potassium, lithium, everything is transported or saved in this mineral oils to avoid this tarnishing. So sodium metal, you have seen like it can show either oxidation or combustion depending upon the availability of oxygen. In combustion, oxygen can be more in quantity, mm, like available in a bit more quantity. So you can say like other than simple oxide, something different with more oxygen can be produced, as you have seen Na2O2. So in combustion of metal, even you can see a yellow flame, and this yellow flame, like it is a result of strong combustion of sodium metal or strong reaction with sodium metal during ignition in the lab. And in some practicals, maybe you are like able to see this directly. After the sodium, you can have an idea like three metals are left. Sodium we are finishing here. Three metals that are left further to discuss while they are reacting with oxygen are iron, copper, and zinc. And we are going to discuss the reaction of these metals with oxygen. So this iron, copper, and zinc, luckily all three are belonging to the same block of the periodic table, and they all together are called the transition metals. So these transition metals are, as we are saying, like these are metals, so definitely if we are discussing with sodium, sodium is a metal as well, but they are more dense. Overall all metals are dense, but transition metals are more dense than sodium metal. As you have seen from literature, the values of density of all these metals. Why transition metals are more denser, you can have a rough idea about the size or volume. Like from this view of the periodic table, you can have an idea that sodium is having a comparatively bigger size or occupying more volume as compared to these metals. You know, like while moving along the period, size is going to decrease. So sodium is the very first member. It is having a comparatively bigger size, and density is inversely proportional to volume. So you can say like these metals are occupying more density because of their less volume, and sodium is occupying less density because of its bigger volume. So now you can have a little bit idea that why these metals are more denser, and definitely they are more stronger because they are smaller in size, as you have seen while moving in the periods in the periodic table. They are belonging to the same period, and they are stronger and they are harder. So transition metals have another very important property that is called the variable oxidation states. Like sodium, it can show either +2 oxidation state or +3 oxidation state. It can form ferrous ion or ferric ion, and how, depending upon its electronic configuration. So if you are coming towards the electronic configuration of sodium, that why it is showing the multiple oxidation states, you can have an idea that this iron, like it is having 26 electrons, or atomic number 26. So if you are looking into the electronic configuration, 1s, 2s, 2p, uh, 3s, 3p, 3d, here electrons are going to fill in the 4s before the 3d, because 4s is more in energy than 3d. So at the end we are filling the electrons in the 3d. So either we can remove 2 electrons from 4s because it is less in energy, and we can get the oxidation state +2, or 1 electron that is present in the 3d can be removed as well, because it is a little bit less in energy after this 4s. So we can get either oxidation state +2 or +3. And this iron filling burns with oxygen. Like if reaction is happening in the form of filling, it burns with orange spark producing a black solid. But with sodium oxide, I want to let you know that we have studied already, it can be a white solid, but here we are expecting a black solid. uh, Here you can have an idea that how iron has showed different oxidation states. Same behavior can be observed in copper and zinc, and both can show the different oxidation states if you are looking into detail, like their electronic configuration and energetics while writing into electronic configuration. But one thing, while looking into periodic table, these metals can be a little bit less reactive than the group 1, because they comes later in the periods while moving into the periodic table, and starting elements of each period, or you can say starting metals of each period, like they are more reactive because of their bigger size and more electropositivity. So you can say like these metals overall, these are like situated together in the periodic table. And after the sodium, so sodium is more reactive than all these three metals, and these are less reactive than group 1 metals or sodium metal. As you can see, like reactivity has a behavior that it is increasing down the group and decreasing along the period. So these metals overall less reactive than sodium, as sodium was showing even reactions at ambient temperature and pressure and showing tarnishing, to avoid which you were using the mineral oil. But here, iron, copper, and zinc, iron, copper, and zinc, like they can't show any reaction at the ambient temperature and pressure. If you are looking into the iron, like with two possible oxidation states, like iron shows very slow reaction with oxygen. Even sometimes it takes several weeks. Like most common reaction of iron with oxygen is the rusting that you can see over the surface of iron. Like it takes sometimes several weeks or months to finish, like, and even it can't be possible only in the availability of oxygen, but it requires an additional substance that can be water or moisture from the air, without which it can't react. So this is showing actually very high activation energy and slow reaction of this iron. So iron is definitely a less reactive metal than alkali metal. So, but if it is formed, it is appearing in the form of this rust color you can see, and this is even visible during the process of rusting over the iron. And but as iron is having two different oxidation states, so this second oxidation state can show a black uh, oxide. And but both oxides are like ferrous oxide and ferric oxide, both are insoluble in water. But you have seen that sodium metal oxide, like sodium oxide, it was soluble in water and was forming a strong alkali. So now you have seen another property of oxides of these metals, like both are insoluble in water, but they are radially dissolving in the strong acids like hydrochloric acid or sulfuric acid. So if we are talking about the copper, like copper can has, like other transition metals, it can have two common oxidation states, +1 +2, and it is not reacting with oxygen at room temperature, but upon heating it can react with as well. Upon heating it can react with oxygen only, and it can show the blue green flame as you can see in the picture. But you have seen like reactivity is less because reaction is not possible at room temperature, but only in the availability of temperature or when you are doing any sort of combustion. So this could be a characteristic test for the identification of copper as well. If you are having any like metal and you are unable to identify, just burn it and you can get this metal with the help of this blue green flame. Copper 2 oxide, it can be available apparently in this black powder form. These two oxides can be available in two different colors, like copper oxide and copper 2 oxide you can see like can be available in the red or black color depending upon the oxidation states. Like alkali metals have another properties, like they can show different oxidation states and different colors even in different oxidation states. Actually it is a different topic, like DD transition, maybe we can study in the future. And if we can have a look on the reaction of like last metal that we are going to discuss here with respect to reaction with oxygen, zinc can react with oxygen, and zinc can form the zinc oxide. But again this reaction is not possible at room temperature. We have to heat it, provide additional activation energy while heating, then we can dissolve this into water. So now you have seen like overall the reactions of zinc, copper, and iron, they were asking for specific requirements like temperature or any other feature that can help to increase the activation energy. So these reactions are having more activation energy or slower reactions, but alkali metal, it is highly reactive. So although all were metals, but you got something like there is the possible comparison of reaction of all these metals. And even these all metals, like they can have a specific color in the flame that would be characteristic. I hope like there are a lot of things that we can compare, but it depends upon your course. Like if you want some more details we can discuss, but from here you can have a general idea that each metal is having a characteristic color in the flame that we can discuss later regarding their electronic transitions if you want. Here your lesson is going to end. I hope you have enjoyed it. If you have got it, its end. Otherwise, you are more than welcome for any question or any confusion if you have in mind. So you can let me know and we can discuss it more. So we are going to finish your lesson here. So enjoy and like try to get it. If you are having anything, you can anticipate it. You can follow and let me know. I can follow it up and we can resolve all the problems regarding this. So it's over. So bye.